In this video, we are going to talk about phasors and phasor diagrams and discuss how useful it is when analyzing circuits powered with AC sources. The figure shows a series RLC circuit that is powered by an AC source. If we use Kirchhoff's voltage rule and sum the voltages around the loop, we get Vs is equal to Vr plus Vc plus Vl, where Vs, Vr, Vc, and Vl are the source, resistor, capacitor, and inductor voltages respectively. The source voltage is sinusoidal, which also produces a sinusoidal current of the form I of t is equal to I sub m sine omega t. In the figure, the current goes around the loop in the clockwise direction. Typically, the source voltage is known and is given by its amplitude and the frequency of oscillation. The resistance, capacitance, and inductance are also known. What we would like to know are Vr, Vl, Vc, and the sinusoidal current. The voltage rule gives us a differential equation as shown after plugging in known expressions for Vr, Vc, and Vl. The resulting differential equation is a non-homogeneous differential equation with a sinusoidal driving function. To solve this equation, you first need to determine the charge Q from which we determine the capacitor voltage. The next step is to differentiate the charge Q with respect to time to get the expression for the current, which then provides us with the expression for the resistor voltage. Finally, we differentiate the current with respect to time and multiply by the inductance L to get the inductor voltage. However, this is a very tedious process, especially considering that the general solution may be broken down into three types depending on the values of R, L, and C. A much simpler way to analyze the series RLC circuit is through the concept of phasors. Phasors is an alternative way of representing the amplitude, frequency, and phase of a sinusoidal function. The function is represented by projecting its amplitude to a circle with constant radius. The radius of the circle corresponds to the maximum amplitude of the function. An arrow is used to represent this maximum amplitude. We call this arrow the phasor. The phasor goes around the circle in the same way that the amplitude of the sinusoidal function changes. Let's say we have a sinusoidal function of the form as shown, that is, a of t is equal to a sub m sine omega t plus phi, where a sub m is the amplitude of the sine function, omega is the angular frequency, and equal to 2 pi times the frequency, and phi is the phase angle. In the simplest case, when the phase angle is 0, the sinusoidal function is 0, 180, and 360 degrees, has positive maximum amplitude at 90 degrees and negative maximum amplitude at 270 degrees. The phasor representing the sinusoidal function at 0 degrees is the arrow at the 0 degree angle in the circle. If we project that arrow to the y-axis of the sinusoid in the time domain, the projection is 0. The phasors at 180 and 360 degrees also have 0 projection in the sinusoidal waveform. The phasor at 90 degrees is now shown, as well as its projection in the sinusoidal waveform. At 270 degrees, we have this relation between the phasor and its waveform in the time domain. We can just as easily get the phasors at the other angles. This short video hopefully will help you gain an even better understanding of what phasors are and what they represent. The blue arrow is the phasor, while the red arrow in the left figure and in the right figure represent the projection of the sinusoidal waveform for various angles. These phasors represent the voltage or current of any circuit element. Thus, in the series RLC circuit, there is one phasor representing the current, another representing the resistor, another representing the resistor voltage, another for the capacitor voltage, another for the inductor voltage, and one more for the source voltage. The phasor diagram that you see in the current slide is actually called an Argand diagram. It's a method of plotting complex numbers. A complex number has two components, the real component and an imaginary component, typically written like this. Z is the complex number, 6 is the real component, and 4 is the imaginary component. The small letter j represents the imaginary component and is equal to the square root of -1. Sometimes the small letter I is used. Thus, to plot this complex number, you draw an arrow with 6 units length along the real axis and another arrow with 4 unit lengths along the imaginary axis. The resultant is your complex number or your phasor. To get the magnitude of the complex number, we simply take the square root of the sum of the square of the real component and the imaginary component. You can get the angle by simply taking the tangent inverse of 4/6, because in the figure, the 4 unit length is the opposite side of the angle and the 6 unit length is the adjacent side of the angle. Now that we understand what the phasor is, let's take a look at the phase relationship between each circuit element. First of all, if the current I of t has a frequency of omega, then all circuit elements should have the same frequency. There is no reason for any of the circuit elements to have a different frequency unless that circuit element has its own driving frequency that affects the frequency of the source. If we consider a phase angle of 0 degrees, then the phasor for the current may be represented by the purple curve in the figure. The voltage across the resistor, represented by the blue curve, should have the same phase as the current. In other words, if the phase of the current is 0 degrees, then the phase of the resistor voltage is also 0 degrees. We know this because as the current increases, the resistor voltage also increases at the same time. The inductor voltage, on the other hand, has a phase that is 90 degrees ahead of the current. As the current changes with time, an inductor voltage is induced, consistent with Faraday's law. A small change in the current induces a small change in the inductor voltage, and a large change in the current induces a large inductor voltage. Thus, at theta equals 0, the change in the current is largest, and therefore the inductor voltage is maximum. Mathematically, the inductor voltage is proportional to the derivative of the current with respect to time. Thus, if the current is Im sine omega t, then taking its derivative will give us Lim omega cosine omega t. But cosine omega t is just sine omega t plus 90 degrees, as you very well know from trigonometry. Mathematically, this means that the inductor voltage is out of phase and ahead of the current by 90 degrees. The capacitor voltage has a phase that is 90 degrees behind the current. As the current changes with time, capacitor voltage changes as well. When the current is maximum, the charges across the capacitor begin to increase in number. Thus, the voltage across the capacitor also increases. As the number of charges increase on the capacitor plates, the capacitor voltage increases further. However, the current decreases because the charges remain on the capacitor plates. When the capacitor voltage is maximum, the capacitor is fully charged and there is no longer any current. Thus, at theta equal to 0, when the current is maximum, the capacitor voltage just begins to increase. Once the capacitor voltage is maximum, the current becomes 0. Mathematically, the capacitor voltage is proportional to the charge Q. Taking the derivative of the capacitor voltage with respect to time, we also get the derivative of the charge with respect to time, which is just the current. If the current is sine omega t, then integrating will give us negative cosine omega t divided by omega. But negative cosine omega t is just sine omega t minus 90 degrees, as you very well know from trigonometry. Mathematically, this means that the capacitor voltage is out of phase and lags the current by 90 degrees. Combining everything we've learned so far, we can now draw the phasor diagram for the current and the voltages across each circuit element. If we consider a phase angle of 0 degrees, then the phasor for the current may be represented by the purple arrow in the figure. The phasor for the resistor voltage can be represented by the blue arrow in the first figure. You can see that the phasors for the current and the resistor voltage coincide with each other regardless of the phase angle. It is plotted on the real axis. The inductor voltage, on the other hand, has a phase that is 90 degrees ahead of the current. It is also plotted on the imaginary axis. Regardless of the phase angle, the inductor voltage always leads the current by 90 degrees. The capacitor voltage has a phase that is 90 degrees behind the current. Regardless of the phase angle, the capacitor voltage always lags the current by 90 degrees. It is also plotted on the imaginary axis. What about the source voltage? This is the advantage of using phasors in analyzing circuits powered by AC sources. Phasors have two components, its magnitude and its direction. You can therefore treat phasors the same way as you treat vectors. You sum all the voltages in phasors the same as you sum vectors. Thus, in a series RLC circuit, the total voltage is the sum of the squares of the voltages of each of the circuit elements, and this sum is equal to the source voltage. From that, we obtain the amplitude of the source voltage. What about the phase angle of the source voltage? Since the phasor for the capacitor voltage and inductor voltage are 180 degrees out of phase, the sum of these two voltages is just VL minus VC. Thus, we can rewrite the expression for the source voltage to that shown. We can then determine the phase angle to be the angle between the phasor describing the sum of the capacitor and the inductor voltages, and the phasor describing the resistor voltage. The phase angle is then the inverse tangent of VL minus VC divided by VR. We can see from this equation that the source voltage does not have necessarily the same phase angle as the current and will depend on the values of the circuit elements. In reality, we typically set the source voltage as 0 phase, and the phase angles of the current and the phasors of each circuit elements are computed relative to the phase angle of the source voltage. Graphically, we would add the phasors the same way we add vectors. That is, we either draw the resultant phasor from the parallelogram method, or we connect all phasors head to tail, and the resulting phasor would be the phasor corresponding to the source voltage. Again, the reason for using this and not simply using simple algebraic addition or subtraction is because the phasors are always expressed in terms of the amplitude and the phase angle of the phasor, and that phasors are complex numbers. If we divide everything by the current, we have the following expression, where Z is called the impedance. Z is called the source impedance, while ZR, ZL, and ZC are the impedances of the resistor, inductor, and capacitor respectively. These impedances are defined in terms of the resistance, inductance, and capacitance as shown in the table. ZR is equal to R, ZL is equal to J omega L, and ZC is equal to 1 over J omega C. R we know as the resistance. The small letter J is the imaginary number equal to the square root of -1. Omega L is called the inductive reactance, while 1 over omega C is called the capacitive reactance. The resistance is also in phase with the current. The inductive reactance is out of phase and leads the current by 90 degrees. The capacitive reactance is out of phase and lags the current by 90 degrees. Based on what we know about complex number, the phasor representing the total impedance can then be written as shown. I hope you've picked up what phasors and phasor diagrams are and how they can be very useful in analyzing circuits with AC sources. Compared to solving second-order differential equations, phasors are equally powerful and easily more facile. I look forward to our discussions in the next video when we tackle parallel RLC circuits and the power triangle. See you in the next video!